Hello, curious minds. Have you ever wondered why a straight stick looks bent when it's half submerged in water? It's like the stick is playing a magic trick, but no one's involved, just physics. This fascinating effect is called refraction, and it happens when light changes its path as it travels from one medium to another. Now, why does light bend? It all boils down to speed. Light slows down or speeds up depending on the material it passes through. This bending follows a neat relationship known as Snell's law, which says the product of the refractive index of the first medium times the sine of the angle of incidence equals the refractive index of the second medium times the sine of the angle of refraction. In other words, n1 sine I equals n2 sine r. Here, the angel's eye and r are measured from an imaginary line called the normal, which is perpendicular to the surface between the two media. Whether the light bends towards or away from the normal depends on which medium is optically denser. That means whether light travels slower or faster in that medium. And to put numbers to this, the speed of light in any medium is the speed of light in vacuum divided by the refractive index of that medium. Symbolically, V equals c divided by n, where c is about 300 million meters per second. So, next time you see a straw in water looking broken, remember, it's light playing a speed and direction game called refraction. Alright, let's get a bit more mathematical, but don't worry, it's as smooth as sliding on ice. Snell's law is the heart of refraction and tells us the exact link between the angle of incidence and the angle of refraction. It says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction remains constant and is equal to the ratio of the velocities of light in the two media, which also equals the ratio of the refractive indices of the second medium to the first. Put simply, sin I divided by sin r equals V1 divided by V2 equals N2 divided by N1. Now, when light moves from a rarer medium like air into a denser medium like water, it bends towards the normal, sort of like it's slowing down and taking a shortcut. But when it leaves the denser medium and goes back to a rarer one, it bends away from the normal, like it's speeding up and stretching its legs. Also, a cool fact, the refractive index is dimensionless, meaning it has no units, and it actually changes slightly with the color of light, a phenomenon called dispersion, plus factors like temperature and the exact makeup of the medium. This explains why a prism splits white light into a rainbow of colors. Picture a rectangular glass slab sitting on a table and a light ray hitting one side. As the light ray enters the glass slab, it bends towards the normal because glass is denser than air. Then, when the ray exits the slab on the other side, it bends away from the normal, returning parallel to the direction it originally came from. So, interestingly, the angle of incidence at the first surface equals the angle of emergence at the second surface, which we can call I equals z. However, even though the emergent ray is parallel to the incident ray, it is shifted sideways, a bit like a car changing lanes but keeping the same direction. This sideways movement is called lateral shift, denoted by d. The amount of this lateral displacement depends on the thickness of the slab, denoted by t, the angle of incidence I, and the refractive index n of the glass. Mathematically, the lateral shift d is given by the thickness t multiplied by the sine of the difference between the angle of incidence and angle of refraction, all divided by the cosine of the angle of refraction. In words, d equals t times sine open bracket I minus a close bracket divided by cosine r. So, the light ray sneaks sideways through the slab before coming out, which is why objects seen through glass sometimes look shifted or displaced, like your reflection in a thick window. Now, let's talk numbers. How do we measure refractive index and what do those numbers actually mean? The absolute refractive index of a medium, represented as n, is simply the speed of light in vacuum divided by the speed of light in that medium. In formula terms, N equals C divided by V, where C is the speed of light in vacuum and V is the speed of light in the medium. Since light slows down in any material compared to vacuum, N is always greater than 1. Next up, we have the relative refractive index, denoted as N to 1, which compares to different media. It's the ratio of the refractive index of the second medium to that of the first, mathematically N2 divided by N1, which equals the ratio of the speed of light in the first medium to the speed of light in the second medium, V1 divided by V2. This relative index tells us how much light bends when going between these two materials. We can find these refractive indices experimentally, either by carefully measuring the angles of incidence and refraction and applying Snell's law, or by observing the critical angle for total internal reflection. Think of when sunlight glints inside a water droplet or a glass fiber cable. These measurements help us understand lenses, cameras, and even the twinkling stars above. Alright, let's dive into what exactly helps total internal reflection happen and what messes it up. First off, the essential condition is that light moves from a medium with a higher refractive index to one with a lower refractive index, and it hits the interface at an angle bigger than the critical angle. Materials are like personality types. Some are more prone to encourage TIR. When the surface of the medium is beautifully polished and smooth, light bounces nicely without scattering, similar to a smooth dance floor making dance moves easier. Rough surfaces are more like a bumpy road that scatters light and spoils the reflection show. The shape of the surface matters too. Flat surfaces reflect predictably, while curved surfaces can focus or deflect light in complex ways. Think of optical fibers, which are like super thin light highways where light zigzags inside due to total internal reflection. Also, how the light rays spread affects TIR. Collimated rays, those beautiful parallel beams, like from a laser pointer, maintain their path better than scattered rays. That's why devices like endoscopes and prisms rely on controlling angles and surfaces meticulously to guide light efficiently. In the diagram, you can see rays approaching the boundary from the denser side at different incident angles. Those below the critical angle partially escape by refraction, but those above it get completely reflected back, demonstrating the magic again. Let's solve a real problem to bring theory to life. Suppose we have glass with a refractive index N1 equal to 1.5 and water with N2 equal to 1.33. What's the critical angle for total internal reflection at the glass-water interface? Using Snell's law at the critical angle, sin of C equals N2 divided by N1, that's 1.33 divided by 1.5, which equals approximately 0.8867. Now, applying the inverse sine function gives C equals arcsin of 0.8867, which is about 62.46 degrees. This means that whenever the angle of incidence in glass exceeds 62.46 degrees, light will totally reflect inside the glass instead of going into water. Imagine being a light ray trap inside glass, no chance of escape beyond this magical angle. The simple ray diagram shows the boundary between glass and water, marking the angles involved, helping you visualize exactly where total internal reflection kicks in. To wrap it up, total internal reflection happens when light travels from a denser medium with refractive index N1 to a rarer medium with refractive index N2, and the incidence angle exceeds the critical angle C, which equals the inverse sine of N2 over N1. This phenomenon is harnessed ingeniously in optical fibers, prisms, binoculars, and even to enhance the sparkling brilliance of gemstones. Importantly, in ideal conditions, there is no energy loss to refraction since all the light reflects back, making TIR an efficient and powerful tool in optics. So next time you see a diamond sparkle or use a pair of binoculars, remember the light is bouncing inside, refusing to escape, all thanks to total internal reflection. That's all for today's journey through the fascinating world of light's hidden bounces. Physics is fun when you can laugh and learn. See you in the next session.